Hello everyone and welcome back to ARTtech Seminar. Our next speaker is Timo Heinäpurola from Reforged Studios, and Timo is going to talk about optimizing rendering pipeline in their new project. Welcome, Timo.
So, hi everyone, and welcome to this presentation. As you already heard, my name is Timo Heinäpurola, and I'm going to be talking about optimizing our renderer for Metal and iOS. But before we go into the actual topics, I'm going to give a brief introduction into the company, who we are, and also on a personal note, who I am and where I come from. So Reforged Studios is a relatively young company. We were founded about 2 years ago by 4 industry veterans, people who've been developing games such as League of Legends, World of Warcraft, Need for Speed, EVE Online, a long list of really high-profile titles. We're focused on mobile games development, and we're based in Helsinki, Finland. So personally, I started in the IT industry that I did for 5 years, developing all kinds of business-to-business applications. But during those 5 years, I still had, the feeling I wanted to be in the game development industry. So I started doing some indie development. And I released one commercial Android game with my own technology, but that didn't really turn out that well. Surprise, surprise. So I moved to Bugbear Entertainment, started working on racing games, and additionally did some work on Ridge Racer Driftopia. But my priority was in next car game Wreckfest, and I was also the lead programmer of that project towards the end of my stay at the company. After that, I moved to Next Games, did some work on Compass Point West, but my main priority again here was to be the lead programmer on The Walking Dead No Man's Land, which was a really interesting project, having the ability to work on such a big IP. So now I'm at Reforged Studios, and I'm basically responsible for maintaining the high-level vision and architecture of our in-house engine. And also do most of the work on that side as well. So the topics that I'm going to be talking about today, I'm going to start off with talk about rendering architecture, so how we architectured our renderer in our engine. Then I'm going to do an overview of tile-based rendering and how we can use Metal to program on those platforms. There's some high-level information here, things that people who are accustomed to using Metal might skip, but for those who aren't, there's some basic information. Then I'm going to talk about tools and processes, some of the tools that we've built in-house and some which are provided by Apple. And of course, optimization tips and tricks, starting from the big things, the frame-by-frame things, and moving on to shader optimization. So it's going to be a relatively technical talk, naturally. So rendering architecture, first of all, the Reforged Studios engine is multi-layered, so each of these layers has their own optimization capabilities. The lowest level interface is architectured around Metal, and this allows us to take advantage of a lot of the architectural optimizations built into Metal itself. The engine is also lean and clean, so we focus a lot of effort into writing code that is easy to understand for existing engineers in the team who haven't been working on the features, and for people, newcomers who will come into the team. So there are multiple layers of abstraction, as already mentioned, 3 to be exact. The highest level is built on top of engine entity components. And these are things, very tangible things that can be understood in layman's terms as well, including models, lights, and cameras, things that you need to define your world scene. Then these components are responsible for populating draw lists, which are passed to the mid-level renderer, which we actually just call the renderer. And the renderer then executes these draw commands found in the draw lists and does the actual rendering operations with the lower level APIs. This level can basically do a lot of optimizations, such as optimizing passes. If you continue rendering into the same render targets, we don't need to create new passes for that, and we can skip a lot of that overhead. We also have type draw lists. So we have a number of predefined draw lists that we can put our geometry into, such as opaque, alpha-tested, alpha-blended, and each of these can be rendered in a predefined order to take advantage of tile-based deferred rendering architectures. And as said, this layer uses the lowest level API, which is architectured around Metal, to do the actual rendering work. And this layer contains things such as function calls for like setting buffers or setting pipeline states, and finally drawing primitives. So very, very low level things. Then let's look at how we render an individual frame. Like, what are the different steps that we take? So naturally, we start off with initialization of our resources. We do this once at loading time, and when the game state changes, we need to switch our resources. So we initialize our resources at that time. Then we do a shadow pass, and we actually do the shadow pass only on the higher-end devices. On lower-end devices, we use shadow blobs. We render PBR linear lighting into 16-bit floating point render targets. Then we use that information and do tone mapping and color correction on that to get final color, sRGB encoded color, actually. Then we render debug information and UI information on top of that. And finally, we clean up all our resources when the game state changes or the application closes. So pretty standard, but gives you kind of a structure for the things that I'm talking about here. So now let's talk about tile-based rendering and what metal is. So tile-based rendering is based on the idea of segmenting the screen. So in a typical immediate mode renderer, if you want to render a couple of triangles, you basically just take the vertices, do primitive assembly on that. You process the vertices, you rasterize the triangles, you get a number of fragments, and then you blend those into the render targets. It's, of course, not that simple for a lot of the modern architectures, such as NVIDIA, which uses kind of a binning system on there, but it's more or less the idea. But in tile-based rendering, what you do is that you split your screen into one or more tiles. And each of these tiles operate only on the data that is required by that tile. So only the triangles that actually touch that tile are going to take part in the processing. So let's look at what the GPU looks like from a bird's eye view. So the GPU has one or more shader cores. Each of these are organized in a SIMD manner. So that means that they have one or more, or multiple actually, a lot of ALUs, each of which operate on the same instruction, but with different data. These are also 16-bit floating point optimized. So if you're using 16-bit floating point math, and you're basically going to use half the registry space, and you're going to save a lot of energy. Because also the registry file is split into 16-bit blocks. So that's very, very important on these architectures. These GPUs also have typically a very small on-chip memory that we use as like the main storage for anything that we need to process on the GPU. So this is what the shader cores typically access. And the idea in tile-based rendering is that we populate this memory with the information that we need for rendering an individual tile. Of course, occasionally we need to access the system memory as well directly, such as for doing texture sampling, but then of course you use your caches afterwards. But the problem with accessing system memory is that your bandwidth is very limited to limit the amount of energy used for rendering. So that is why we try to operate mostly in on-chip memory. So the operation flow in tile-based rendering goes roughly like this. It starts with vertex processing. So when we start rendering, we know all the individual vertices that we need for rendering that frame. And we do processing. We process those vertices, run the vertex shaders, and stuff like that. Then we do tiling, and we select which of the vertices affect which tiles. And we build what's called a parameter buffer, which is a compressed buffer that contains a list of lists. A list is the tiles, and these tiles then contain a list of geometry that needs to be processed for that tile. Then for each tile, we do rasterization. So we pull in all the data from the parameter buffers that we need for rasterizing. And now on tile-based deferred rendering architectures, which the PowerVR architecture, for instance, is, we also do hidden surface removal. So we render all the opaque geometry into the Z buffer, and then we use the Z value for each individual pixel to determine which pixels actually need to be shaded. So this is why it's so important to render opaque first. Because as soon as you start rendering any alpha-blended stuff, this cannot be done anymore. So it only works for opaque geometry. Then, of course, we do shading for all the pixels that we need to shade, alpha testing, and alpha blending. So what is metal, then? Well, metal is, it's closer to metal. It's a more low-level API than VULKAN or DX12, than OpenGL-ES, but it's not as low as VULKAN or DX12. It's based on immutable states. So all the validation of those states is done when the states are created and not at render time, such as what is done in OpenGL-ES, for instance. You get a lot more control into your pipeline, and you also get a lot more visibility into that. So you get to control things such as render, surface, load, and store. You get to say what happens to a surface when you start rendering to that. Do you need the existing content in the frame buffer when you start rendering into that? Are you doing alpha blending, for instance, on top of that? And what you need to do to it when you're done rendering that? Do you need to store that back into system memory? Resource allocation, you have a lot more control over that. You can, for instance, allocate multiple textures to alias the same memory, which was actually added in, I think, iOS 10, like Metal 1.2. So one of the major benefits of Metal is also that it's updated with pretty much every iOS update. And iOS updates also are typically available for older generation of hardware as well. So this means that we need to build a lot less specific optimizations for specific hardware sets and for different platforms, because we can expect that people are going to have those updates. The Metal command flow starts with acquiring a command buffer from a command queue. So the command queue is what orders the execution of these individual command buffers. The command buffers then contain the individual draw functions and state sets and all of that. Then we acquire a drawable, and drawable is basically the final render target on the device that can be presented on the screen. So there's a relatively small amount of these drawables available on the GPU, so we need to be careful with acquiring them. Because the drawable, it will be locked as long as we have outstanding GPU operations on them. Then we create a command encoder, which is responsible for writing the commands into the command buffer in a state that the GPU understands, or in the form. Then we use this command encoder to write our draw calls in there. And finally, we end encoding. But it's important to note that the GPU commands will not yet be sent to the GPU at this point. After this, we can register a command execution finish callback, which will be called when all of the operations in the command buffer have been executed. And finally, we commit the command buffer. And at this stage, it'll be transferred to the GPU for processing. So Metal does have some rough spots. It's not perfect, of course. For instance, it does not have a dynamics extension mechanism, which means that using the new features requires building against a new platform. And then again, supporting multiple platforms leads into a preprocessor jungle. Metal shader code is also a black box, so it's not documented anywhere. So you can't build your own tools for analyzing it. Function constants that I'm going to be talking about later in this presentation are a really good tool or really good functionality, but they're not as powerful as preprocessor defines. Then again, using preprocessor defines is really heavy at load time. Error reporting of GPU errors is also limited, so you do get some information. When your command execution finished callback is called, you get potential errors that have happened on the GPU, but the information in that data is very limited. And of course, we're only talking about Apple technology here. So a couple of things about VULKAN then, like comparing that to Metal. How is it different? Well, VULKAN does have an extension mechanism, but it's a lot more complicated to use and set up. So it's something like 1,000 lines of code or something to actually set up VULKAN. And compared to Metal, Metal isn't really like that many lines actually. It does give you a lot more low-level control over your resources. So a texture allocation, for instance, is a 3-step process. So it's very complicated, but it gives you a lot more control. Also, you get to have more control or more powerful tooling because of the openness of the platform as well, such as the shader language, the intermediate shader language, which is an open standard. So Metal 2 was announced at WWDC this year, and it has a number of cool core features, such as argument buffers that I have a couple of mentions in this presentation, setting resources in shaders that is supported on some platforms, raster order groups for manual alpha blending, more control over the performance of that. But there is an increased divergence between OS X and iOS on here. So some features, such as multiple viewport rendering, is only supported on OS X. Of course, this is relatively natural because that's for VR. But still, there's that problem coming in now. Some features have been brought from iOS to OS X, such as direct-to-display, that I'm going to be mentioning in this presentation, or going to go into a bit more detail, actually, in following slides. So that's a cool feature. And of course, you have a significantly improved tool set as well. So a couple of words about argument buffers. The idea is that you can embed your resources in your constant buffers. So it's stored in the same way as constant buffer data, i.e. in an MTL buffer, but you use an encoder to write that data into that. So for instance, you have a texture reference that you want to put in your argument buffer. You use the encoder to set that value in the argument buffer. This encoder is acquired from a shader. So you actually have to have the shader that is using that argument buffer to get the encoder, which can sometimes be a bit difficult from an architectural point of view. And during rendering, you need to call use resources just to specify, tell Metal that this is a resource that you're using during rendering. Support of this is in 2 tiers. So the first tier supports things such as texture referencing and buffer memory referencing, if I recall correctly. But the second tier is only supported on non-iOS devices. So that'll be OS X devices for you. tvOS also doesn't have it. And the idea here is that you can change your resource data and your resource references on, say, a compute shader. And you can generate these really complex procedurally generated environments with that and change the materials on the GPU and never leave the GPU. Just continue rendering on there. So it's very, very powerful, but only supported on some platforms. And I have a couple of tools that I wanted to mention here that have come in Metal 2. I'm not going to be talking too much about them here, though. But we have GPU performance counters, so we can actually see what happens on the GPU in more detail. We have information such as cache miss rates in your shaders and shader occupancy information that can explain why your shaders are running poorly if you're using too many registers, for instance. Then you have a render target pixel inspector, which is actually something that's been requested for like years and years already, but Apple hasn't implemented that. And now that they've done it, and they got pretty good applause at WWDC this year about that. And then I have a reference slide towards the end of the presentation that has a lot of links to different presentations, mostly from WWDC. So that has a lot more information on that. So please check that out. So now let's talk a bit about tools and processes. So the first thing that we did in our engine is that we support deterministic profiling. So we have a regression testing framework that allows us to execute individual script calls at specific times or ticks. The game code also supports this by having deterministic game code. So we can define this test case script that executes events at specific ticks, and then we can expect the game to behave exactly the same, and we can get really predictable timelines for performance optimization. We also have a pause feature. We can pause the game at any time. We also pause all our effects and everything, and we can gather information about application performance for that frame. Then we have an isolated static scene. So that was a really difficult sentence. Isolated static stress test scenes where we can spawn individual animated models and also spawn effects that freeze at their most expensive time. So we can specify when we freeze those effects. Really, really useful. So one tool that I've been using a lot is Metal System Trace. It exposes a lot of the information what happens on the GPU when you're rendering. It has multiple tracks. It has tracks for showing you what happens on the CPU and also what happens on the GPU for vertex processing, fragment processing, and when your results are being displayed. So if you hit those individual vsync points there, we know that we're running at 60 frames per second. Then we have frame capture. And it has multiple panes for different kinds of information. The first one here is frame events. So it displays which individual events are happening on the GPU, all the encoders that are being executed on there. Also shows their performance, how long it takes to execute these encoders, and an overall frame counter, just like general information of application performance. Then frame properties, what are the bound vertex buffers, at which point your render pipeline statistics and all of that. And you also get to see which resources exist on the GPU and what are the color formats of textures, their sizes, and all of that. And then you have Shader Debugger. This is one of the most useful tools, I think. It displays what shader code is being executed for a draw call, and it also displays how it's performing on individual lines of code. And you get to change the shader code and re-execute all the draw calls, and you immediately get updated performance statistics. Sometimes it doesn't work, but mostly it does. So now let's move into the tips and tricks. Start with the big things. So first of all, you need to pay attention to your pass counts. So the reason for this is that individual passes have a relatively high overhead on tile-based deferred renderers. You need to copy in your input data into tile local memory, and you need to copy that back as well over a relatively low bandwidth memory bus. There are two ways of getting around this, of minimizing your passes. First of all, of course, kind of a no-brainer way, just continue rendering if you render into the same render target. But the more tricky one is when you need to do post-processing. So one thing we did here is already mentioned that we're doing PBR rendering. So our simple method, our naive implementation, renders the scene into a 16-bit floating point RGBA texture. And then it does tone mapping on that texture, producing the final BGRA render target. So we merged these two passes. And the way we did this is that we used programmable blending. It's a feature supported on PowerVR chips, mostly just PowerVR. Not a lot of chips actually supported. But in Metal, it's very easy to use. So you just define a structure that has, in our case, has two colors. The first one is bound to the 16-bit floating point render target, and the second one is bound to the final drawable. Then we render the scene into the first one, and for the full screen post-processing pass, we read the first one and write out the second one with the processed color. So we return another instance of this fragment, and we get this fragment data. We get this as an input to the shader. So very, very simple stuff. So triple buffering. Why should we do triple buffering? Well, memory on graphics resources is shared between CPUs and GPUs. We're operating in a shared memory architecture. So rendering is also performed one command buffer at a time, and the command buffer is locked for the execution of that command buffer. So the CPU will hang if it doesn't have any command buffers available. And there is a communication latency between CPU and the GPU. So how we do this is that we allocate 3 command buffers and 3 matching dynamic data buffers for all this dynamic scene data, and then we use them in a first in, first out manner. This overall hides wait times. So here's a schematic that basically explains what actually happens here. So we start writing it to buffer 0. We're done with that. We commit that to the GPU. But it takes some time to start executing. So we need another command buffer for frame 2. So we start encoding that. But when we're done with that, the first one might actually not yet be done on the GPU. So we need a third one. But when processing or generating the third one, we get a notification that the first one is already done on the GPU. So we can reuse that. So having 3 command buffers, basically looping it like this, removes the waits that we have if we're running at, say, 60 milliseconds on CPU and GPU. So now a couple of words about dark to display. So the desktop compositor uses the GPU for compositing the scene. Full screen applications typically don't require this, though. So it's possible to circumvent this system by setting up certain parameters during rendering, so you don't manually enable it. But so I'm actually going to skip through these because we're running out of time. But there are a number of things that you need to take into account to make sure that the GPU uses direct to display. So finally, couple of tips about shader optimization. First of all, remember that registry usage is really important. So shader threads are dispatched in large groups, but they're only executed in small SIMD groups, so smaller groups of operations at a time. And the rest of the threads basically go for coffee at this time. The GPU then schedules these lazy threads when the executing threads are waiting for something, say a texture fetch. But all of the contents of each of these individual threads needs to fit into the registry file. So when you're using less registers, you have better what's called occupancy. So you're more likely to keep the GPU busy. Function constants are one really good way of removing executable code. So you build your shader once, and then you specialize it at every query time. And our materials, for instance, contain multiple specializations, such as for depth-only rendering or using normal maps or whatnot. You can use your function constants in conditionals, and if those conditionals fail, then that code will actually be removed from the code. It's not going to have any overhead. But you cannot modify your input structure layouts that you use for sampling individual constant buffers. But you can, for instance, loop the amount of, or change the amount of vertices that you loop over when you're doing vertex processing, something we do. So then a couple of words about, finally, towards the end of the presentation, about memory and textures. So in metal shaders, you need to pay attention to how you're addressing your memory. You need to use the correct address space for accessing memory. Use the device address space for accessing memory that you have a lot of, or data that you have a lot of, but you rarely use that, so there's not a lot of reuse. And then you should use constant address space for all the data that has a lot of reuse, but you have very little of, such as like your materials, and device memory for vertex data, for instance. Also use integer types that have a range, data range smaller or equal to a 32-bit signed integer, because the GPUs have indexing or have memory access instructions that take a base address and a signed 32-bit integer as an offset. And it can't use that if the value doesn't fit into that range. GPUs will also vectorize reads. So if you're using two values close to each other, place them close to each other. And this is actually new in iOS 10. So stack memory. Don't use stack memory. Stack memory you have very little of on the GPU. It has very little memory in general, but very little stack memory because it's split over all the individual threads. So this, for instance, is something where it happens. So this is what's called a dynamic stack array. So you should really pay attention to not follow these kinds of patterns. But do note that GPUs generally do not support functions. They're unwrapped, unrolled. So you're safe to use your functions. Texture sampling. Use mipmaps and compression. Again, kind of a no-brainer, but still very important because it reduces your cache misses and the bandwidth that you use for sampling textures. Also use half floats for sampling, because this way, as mentioned, you're using half the registry space. But the compiler reorders your sampling to happen as early as possible, so you don't need to pay too much attention to where you sample your textures, other than flow control cannot be crossed if it's not constant. So only constant checks can be crossed because the code will be generated at compile time. Then I wanted to mention environment maps, one trick actually that we do in environment maps. First of all, the obvious thing, use cube maps. But we use RGBA8 textures instead of 16-bit floating point textures. The reason for that is less memory used and less bandwidth used. So you might, at this point, you might think that, well, it can't fit HDR values in there. Well, basically it can, but we get around that by scaling to 0 and 1 range. So we select the maximum component. We divide the RGB color with the maximum component, and we store the maximum component divided by 8 in the alpha component. And then we restore this in the shader. So it crunches down all the low values of, say, you have really bright red. It basically crunches the values down. But it works really well for really bright whites. So we haven't really had any problems with this, but it saves a lot of memory, it saves a lot of bandwidth as well. So here are the references. Imagination blog, that's actually a really good resource for anything if you want to learn more about Power VR, which is the architecture that is currently used still on iOS devices. It's Apple has announced that they're developing their own GPU, but when that actually comes to market is a different thing. So this is still valid information, probably for a long time. Then a number of WWDC presentations from consecutive years for optimizing and for different tooling that Apple provides, something I found really interesting and useful. So we have quite a lot of time, actually, for question and answers here. There's my Twitter account. If you want to follow me, I tweet quite a lot. So if you have anything you want to ask, just PM me or send me a public tweet or whatever, and I'll try to answer that. And the company website if you want to know more about that. So yeah, that's it. Thank you.
Do we have any questions? Do note that our lovely sponsor Remedy has some free quantum breaks for all the brave members of audience who make a question. So if you want a new one, just ask something. We don't judge the questions.
Any questions?
Thank you. How exactly are the tiles visible in metal code? Like, do you dispatch separate commands for each tile separately, or is it something that happens behind the scenes?
Yeah, so the question is, how are tiles visible in the API, Metal API? Do you need to take that into account? Well, not really, because like Metal is also built so that it supports non-tiling architectures as well. So that happens mostly in the background. But it basically, the GPU or the driver itself orchestrates that, so you don't really take that too much into account. But there are a lot of features such as memoryless render targets that kind of implicitly bring that up front. So memoryless render targets are something that specifies that a texture will not have a backing store. So it's only used for temporary information such as depth buffers. You can, for instance, if you're using a depth buffer, you know that you're not going to need that information for anything other than basically just doing hidden surface removal for rendering the frame. So you can discard that information. And you don't need to load that from system memory at any point. So you can use a memoryless render target, in which case it'll only use the tile local memory on the chip for all of the operations. So it's more implicit. It's not specifically something that you need to do personally.
Any more questions?
So, are there differences between the Power VR tiling and the desktop video cards from Apple?
Well, yeah, the question, I guess, was that are there differences? Yeah, are there differences in like Apple device desktop GPUs and the iOS GPUs? Generally, the desktop GPUs are non-tiling, so they're immediate mode renderers. They use NVIDIA and AMD. I think nowadays it's AMD. Before it was NVIDIA on the desktops there. As I mentioned earlier in the presentation, NVIDIA has some kind of binning structure where it basically groups draw operations into smaller groups and executes them in a batch and does kind of tiling in the background. But that's something that they only recently said that they're actually doing, and it's totally like in the background. It's not, you don't really take that into account in any way. So yes, they are totally different. Different from architecture, different from like performance characteristics. Like for instance, on immediate mode, it's not the end of the world if you don't exactly render opaque first and then alpha blending after that. But the hit on tile-based renderers is a lot more significant.
More questions?
Yes. How much of the code is run by CPU, and when does it start affect GPU?
Well, yeah, the question is how much of the code is run on the CPU as compared to like on the GPU. In Metal, it's mostly the GPU, because the idea in Metal is that a lot of the manual labor, or a lot of the labor that was previously done by the graphics drivers, such as OpenGL drivers, has been moved to the user. So the user is expected to create valid states and do that beforehand, and then just basically pass that to the GPU. So it's a very thin layer. And I don't know if you recall, but in one of the frames where I showed the Metal system trace, there was the CPU thread and the GPU threads. And the CPU thread actually, even though it is a relatively large block, it has very little operations in them. But the block that actually shows there displays when we started encoding and when we ended encoding. But most of that code is not Metal code itself. So the driver code is very small, is a very small piece. And that's what you really need to take into account, that you don't start doing your operations too much beforehand because of the drawables. But the idea is that Metal contains very little code, and you do like most of the validation beforehand, and then you execute like most of the overhead is now on the GPU itself. And I want to mention that with argument buffers, it's even more so, because typically for like typical Metal rendering, you have somewhat of an overhead for specifying individual textures for individual draw calls. But with argument buffers, it's mostly removed because the argument buffers already contain the states required for the draw calls. So you just specify that you need this texture for rendering, but it's not as heavy as what you had to previously do and bind individual textures for each individual draw call. So it's getting less and less what's happening on the CPU and more towards what's happening on the GPU.
Another question. How about the tiling system? How does it compare to DirectX 12 tiling?
It's not really affected. Like it's the GPU itself. You could have like any API for programming for that. You can program PowerVR chips with VULKAN, or if you would have a platform that supports DirectX 12, you could program using DirectX 12 for that. So the API is still an abstraction layer on top of that, and the driver does do the actual glue code that binds the more or less generic API. It's more detailed, but it's still generic compared to what the driver does. For drivers, basically, it's like getting this block and fitting it here, and that's pretty much everything that it does. It builds a stream of commands. So yeah, but that's very low level.
Any more questions? If not, then thank you, Timo, for the lovely presentation.
Thank you very much.